Occasionally there might be benefits in a study to having different numbers per group. So for example, if chloram was seen as a treatment that might give nasty adverse effects, there might be a benefit to having a smaller number of animals in the chloram group than the control group. So if we go back to the simple experiment we had with just comparing chloram with control without the strains, and assume that perhaps we'd like to have twice as many mice in the control group as the chloram group, so to reduce the number of mice that are exposed to the new treatment. Then it is possible again to adapt the calculation. I won't go into justify how this was done, but you can set the ratio of a number in the larger group, which is for us controls, to the smaller group. We'll set that ratio to be 2 here, and the formulae just builds in this R value, the ratio value. So we've just got R plus 1 on the top and R on the bottom. And so if we put that into a value of R2 into the calculation that we had originally, where we was trying to get a difference of 0.5 in red blood cell count, we come out with needing that the number of mice in the smaller group, here the chloram group, is going to be 7.14, and we would round that up to be 8. So we need 8 mice in the chloram group, so that's a bit smaller than we had before. We had 10 mice before. But we need double that in the control group. So we need 16 mice in the control group, and in total that's going to mean we need 24 mice. So there's always a bit of a price to pay. We're going to need more mice than we had before, but fortunately we're going to need less mice in the group that were treated actively. So you can play with this a bit, but you can't obviously reduce the number that are going to get the active treatment too much. If you say, okay, well, I'll have kind of 5 times as many in the control group and really restrict the number in the chloram group, you would find the total number of mice would be quite a lot more to achieve that, and you need to think about whether it's actually worthwhile to do this, because you are going to be using a larger sample size overall. The most efficient design has got the same number of animals in each group, so it's only if there's another reason to have one group smaller than the other that it's worth considering. Another situation that might crop up is that there's clearly different amounts of variability in the groups, and you know about this in advance. So supposing we knew that one of the groups was going to, well, perhaps that's the active group, the results were going to be variable as to how they responded to this active intervention, and there was a greater amount of variability compared to the controls, which varied less. So the formula is quite easy to adapt for that. If you remember before, in this formula we just had 1 sigma squared. We had the standard deviations, overall standard deviation squared, and there was a 2 at the front of the formula. Now, instead of using that 2 and the overall standard deviation, we just sum up the squares of the 2 different standard deviations. So very similar formulae. If we put that into the calculation for the chloram study, we get that the number of mice per group is 10.79, so that's what we get, and we would round that up to be 11. So there's a bit of a penalty to pay for the fact the variability is different in the 2 groups, and we'd need 11 mice per group. And it's quite nice to be able to take that into account if you think if you're sure your variability is going to be different between the groups.